Welcome to today's InnoTalks session, which is about time-sensitive networking, or TSN. Like many of our InnoTalks topics, it's been getting a lot of press coverage recently as one of the emerging technologies with the potential to have a transformative effect on both the automation industries and on the convergence of OT and IT systems. But why is this? In this webcast, we'll be discussing the problems TSN solves and how it does it. We'll be giving you some feeling for where it should, and just as importantly, shouldn't be applied. And we'll be looking at what a practical implementation strategy would look like given the brownfield nature of most industrial deployments. We'll also do a bit of crystal ball gazing into the future of both the core technology and of the industries that adopt it. Hopefully, by the end of today's session, you'll have a better understanding of the benefits TSN can give you and where it will bring you the most benefit. Essentially, what adopting TSN will enable you to do that you can't do today. We'll also look at how it achieves this, what it can and can't do, and how to start implementing TSN in your applications. Of course, we'll also let you know what we're doing at Advantech and how we can help you along this journey. To help me, I'm joined by two gentlemen with a wealth of relevant experience. Brendan Maluli is Advantech Europe's Business Development Manager for Connectivity Solutions. With a strong background in network communications, he'll help to explain how the underlying technology works and why it represents an evolutionary step rather than a revolutionary one. Peter Lutz is the Director of Field Level Communications at the OPC Foundation. He'll be helping us understand how a TSN infrastructure can be leveraged by the application and communication layers that sit on top of it to provide real end user benefits. Gentlemen, welcome. I'd like to start by identifying the problems that TSN addresses. Peter, perhaps you'd like to pitch in here.
Yeah, actually, when we look at the today's situation, we recognize we have very different real-time Ethernet solutions that have been developed and that are used in the industry. And although they are all part of international standards, at least most of them, they are all incompatible with each other. Typically, as soon as they want to achieve a certain performance, they need specific hardware, not the standard Ethernet controllers. And in addition, most of them even cannot coexist in a common network infrastructure. So this has led to the situation that we have different ecosystems built around some of the major automation suppliers. But this has now raised an extreme complexity and also significant costs for users and suppliers that deliver and need to support these different ecosystems. And this is where TSN comes into play, because this is a technology that is able to harmonize, so to say, this situation.
So we're talking about a common communications infrastructure for an entire system that covers not only the time-sensitive or the time-insensitive IT and soft real-time monitoring needs, but crucially can also provide for the hard real-time elements in the production process. That's obviously paving the way for greater digitalization across an entire business, which in turn is going to produce economic benefits. So if TSN is emerging as a solution for this, what exactly is it and how does it work? Brendan, perhaps you can help us with this.
I sure can, Tim, and thank you for the invite, and thank you, Peter, for the great introduction there. Ethernet, as we all know, is the dominant communication technology. We're used to it in the world of enterprise, MIS, in the world of OT automation. Obviously, it has superseded the older field bus standards based on RS whatever. Ethernet's great. As Peter mentioned right at the beginning, Ethernet is a standard. And the key thing about being behind or using a protocol or a system that is a standard is you have total interoperability. And of course, for the users, the benefit there is because it's a standard, everything gets a little bit cheaper because we have many competitors out there. And Ethernet's great. Ethernet works brilliantly, but the problem with Ethernet is it's not what you might describe as deterministic. Ethernet is what we call a best effort delivery system. We have QoS standards, which have obviously helped, but in the world of industrial automation, QoS may not cut it.
Okay, so what do you mean by best effort?
Best effort essentially means Ethernet from its early days was essentially a shared media system. Then we moved on to Ethernet switches. Then we developed quality of service standards. But still at this day, I cannot with Ethernet guarantee that data from point A will be delivered to point B within a certain time frame.
Okay, and TSN addresses this, but how does it do it?
Well, TSN, the way TSN has been developed is to essentially allow Ethernet to become deterministic. Deterministic essentially means that, as I said earlier, delivery from point A to point B can be done within a certain time frame. The TSN standards allow this to happen based, as I said earlier, on the typical IEEE standards.
And actually on the network, what's happening? There's doing something with slicing packets up differently or something, isn't it?
Yeah, absolutely correct. I mean, what we're essentially doing with the Ethernet frame or the Ethernet bandwidth, and as we know, Ethernet started off at 10 megabit per second, and now we're moving up to 100 gigabit per second, which, obviously in the automation world, we won't see yet, maybe in the future. But essentially, what we're doing with TSN, as you said, Tim, is we're taking the Ethernet data flow and slicing it into portions. Time slicing would be a typical way of describing it, but we call them essentially streams within the world of TSN.
Okay. And they get synchronized across all the units that are in the TSN network by some central clock. What about redundancy? Because it's all right having deterministic data, but it's still actually got to get through if it's mission critical, right?
Yeah, absolutely correct. I mean, you hit the time slicing or the time synchronization. Obviously, if you have a series of, for example, switches in a line, when you have the stream coming through, obviously each switch needs to know what time segment the stream needs to be in. So you're absolutely correct with the time synchronization. When it comes down to the actual slicing itself and the delivery, yeah, it exists and it's happening now.
Okay. Um, and as you said, it's covered by a suite of standards. It's not just a single one. There's actually a whole load of different standards that go to form the TSN network. You've spoken about hard real time. What sort of levels of latency are actually achievable?
Well, again, I mean, it depends literally on the hardware you're using, but we're looking at roughly latency on a high priority stream of between 1 to 2 milliseconds. The key thing, though, is on the actual Ethernet data stream. With a high priority stream, we're offering 125 microsecond for each time segment that can come through. Latency is obviously one of those great things which can be difficult to measure. If you go in port A, out port B, that's easy to measure latency. But if you have several devices in the connection, obviously latency is more difficult to measure. But at the end of the day, we're aiming for 1 to 2 millisecond delivery, which is aimed essentially for the challenges we have in a lot of automation style applications, motion, safety, synchronization between machines on the factory floor, or, and as Peter will talk about later, synchronization across the IT level between factories as well.
Okay. And what's the impact on the remaining traffic? If we're reserving time slices for the high priority stuff, there's got to be some trade-off, right? Presumably everything else runs more slowly.
Yes and no on that one. Essentially, what we do when we create a TSN connection or a TSN link, there is something we call a guard frame available. Into that, we can put the non-TSN traffic. That will be transmitted. So that's one of the great things about TSN. We can bring a TSN installation into a factory, into an automation system, and still yet the standard Ethernet traffic will be delivered within acceptable Ethernet parameters. It's just the key thing with TSN is the ability we have with the standards to be able to deliver time critical, important information within specific windows or specific latencies.
Okay. So if it's an extension of the current Ethernet standards, can it coexist with an existing Ethernet deployment, or does the entire network need to be TSN aware for a system to work?
No, it will happily coexist, Tim. As I mentioned earlier on, we can put existing Ethernet frames through a TSN infrastructure, be it switches, be it, for example, IPCs or whatever. We can do that. This is not like you have to rip everything out of your factory, everything out of your machine, and build in new devices. It will happily coexist. And one of the key things behind TSN as well is we do communicate, or we do work with the higher level industrial management protocols. For example, Peter, with the OPC UA Foundation, with their work with TSN and the IEEE.
Okay. So presumably all of this doesn't just happen. There has to be some level of user configuration involved. How's that done, and what are the pitfalls to be aware of when you're configuring a system?
Yeah, obviously you need to configure something. It's not like you plug it in and it suddenly works. The simile I often draw when I'm talking with people about TSN is IEEE VLANs 802.1q, for example. You need to configure VLANs on the switches for VLANs to work. It's a similar approach with TSN. The TSN traffic has to be identified. It could be port-based, layer 2, layer 3 based, and then prioritized within the TSN system. Now, one thing Peter will talk about later is the IEEE is working on standards whereby we will have like a template, you could say, specifically designed, for example, since automation is the main target for TSN at the moment, template designed for automation TSN time-sensitive delivery.
Okay. Peter, what Brendan's been talking about has all really been network layer 2 stuff. What happens when we start looking at the higher levels in the communication architecture? For example, how do you leverage TSN in OPC UA?
Yeah, for us, for the OPC Foundation, TSN is really a key enabler in order to extend the use cases and the areas of application that OPC UA is already covering today. OPC UA with TSN allows us really to bring our technology into applications that need deterministic behaviors, that need real time. So motion control, distributed real-time IOs, also process control. And we have a dedicated initiative that we started a few years ago, the FLC initiative, which is working on the extensions of what we call the framework, the OPC UA framework, to extend OPC UA for all these field level related applications. And this includes functional safety, motion control, and highly leverages certainly TSN. Even OPC UA itself is transport agnostic and certainly can still run without TSN and will run with other technologies in future as well. And what I think is also important to mention, that this is really supported by all the major automation suppliers. So this is not bringing up just another ecosystem, but it really drives harmonization. And the approach is to have one solution that is supporting factory as well as process automation.
Okay, and you've spoken about a lot of stuff that's happening down at plant level and at the actual process level. How does it help with IT/OT convergence and digitalization?
This is an excellent point, because as I said, it's not just about creating another ecosystem now using TSN. In the past, you were using real-time Ethernet. The vision is really, it's the vision of the OPC Foundation, but actually of all the initiatives that are named Industry 4.0 or the Industrial Internet of Things, to really drive a complete, let's say, consistent, interoperable solution that fully scales from the plant, from the field level up to the cloud. And for this, you certainly need technologies like TSN, because this is the basis, this is the foundation. But we need certainly a standardization on all the different levels. That means we need a harmonized application layer. We need common semantics, because finally it's about what is the meaning of the data. How do we come to vendor independent information? And this is where OPC has, let's say, an ideal solution, including security, including the information modeling. And then it helps to solve these challenges with the industrial interoperability.
Okay, that all sounds great in theory, but what does this look like in real life? Could the two of you walk through a typical brownfield installation like we see in the automation industries? You know, what has to be upgraded? What can be left? How's the migration managed?
Well, the migration's pretty straightforward, Tim. At the end of the day, TSN is Ethernet. So at the physical layer, layer one, what our installers and users are used to, it's the same, absolutely the same. The TSN switches, for example, which Advantech are getting heavily involved with, again, it's a switch, everybody's used to that. Obviously, as I talked about earlier on with you, Tim, we need to be able to create the necessary rules and regulations for the TSN streams or the time slicing or whatever you want to call it. And that's where people do have to get involved. Now, Peter mentioned, I think, at the end of his speech earlier on, or his comments earlier on, that we are generating profiles. We are generating the ability for a user to essentially implement a TSN infrastructure and then have essentially what you might describe as a template which enables them to classify and control the traffic they want over the TSN network.
Maybe I'm also jumping in here, talking a little bit how a migration towards TSN could look like. We certainly can still keep existing installations, for example, machines that are using now the existing technologies with the different real-time Ethernet standards I was talking about. So in our view, we believe that in the first step, for example, such machines could be connected with a TSN network. We could establish OPC UA to drive more that what we call the horizontal connectivity, horizontal communication, including certainly the scaling up to the edge. But this is just then a first step, because in the next step, certainly TSN will move into the machines or into that specific installations. And with this step, then we bring really harmonization into the machines. This is more the vertical piece, also including now the higher layers and the semantics with OPC UA and the different companion specifications. And then we really achieve one consistent solution that is fully scaling vertically as well as horizontally. But it's a step-by-step procedure. So it's not, I think Brandon made this clear, it's not a so-called disruptive technology. So we need not throw away all the investments, but we really can do a step-by-step migration towards TSN.
And when we're talking about not replacing everything, presumably there's still a place for sort of the protocol translation devices we've spoken about in the past, right?
No, absolutely correct. And, my point, and Peter, thank you for emphasizing it. This is not like you have to throw everything away and rebuild everything from ground zero. It's a continuous upgrade capability. We can use TSN, for example, within the machine, even if the endpoints are not TSN aware. And as Peter mentioned earlier on, though, we're already getting into the situation where the endpoints, for example, IPCs, also now are coming out that are TSN aware as well. It's a gradual evolution, no questions about it. And, we understand Peter probably better than I do, and Tim much better than I do, since you've been working in the industrial market a lot longer than I have. Change comes slowly. And the key thing behind TSN is it's a gradual implementation. It's not like a big bang, everything has to go. No, we can move forward slowly but surely on the implementation. And obviously, from Peter's side of things, integrate into the higher level management protocols like OPC UA, for example.
Let me maybe mention one still, let's say, existing challenge. I would call it a challenge. Now, as we all move towards TSN as that common network infrastructure supporting these different protocols, sharing, let's say, the network and the bandwidth with all the different types of traffic and streams. There is still, and Brent mentioned that term profile before. Certainly one important precondition that this finally works is that all the different players in the industry are somehow agreeing to a certain profile. This is for automation, the 6802 activity, joint effort IEC and IEEE, because TSN is something like a toolkit with different mechanisms. So there has to be a common agreement how to use that TSN toolkit and these standards, because otherwise you would have different, let's say, variations of TSN, and this is not helping us, right? So we really have to agree on how to use TSN in a common way.
So if this common profile still needs to be agreed, is that a risk for early adopters?
Oh, absolutely not, Tim. I mean, the profiles are essentially based on the IEEE standards for TSN, of which, if I remember correctly, there's 10 of them, including the redundancy profiles. So the actual physical side of things is all defined, everything's ready. And as Peter mentioned, what we're doing, or what the IEC, IEEE are doing, is essentially generating a template of how to implement TSN in, for example, a machine for motion, for safety, machine communication, inter-machine communication on a production line. So there's absolutely zero risk.
Okay, so the standards exist, equipment's available, and there's no real downside to being an early adopter. So if a company jumps in now and implements a TSN network, what can they expect in the future from a technology standpoint? Brendan?
Well, obviously, I mean, yeah, TSN was actually based upon the audio-visual broadcasting standards the IEEE developed a fair few years ago. Essentially, the best way to look at TSN is its time-sensitive delivery. At the moment, and today, obviously, we're talking about implementation of TSN in automation, OT style environments, which is absolutely critical. There's a lot of time sensitive data running around, as Peter and myself have spoken about, but there's other areas where it's important. For example, transportation, Ethernet train backbone systems. A train is a very complicated device, as we all know, and there's lots of cabling in there. There can be up to 4 networks sitting within one train. Wouldn't it be great to be able to just create one network? Other area which is of interest, and this hooks in nicely to the developments in the world of cellular communications, is 5G. 5G, we have various standards and it's still being rolled out. But one of the things 5G promises to bring is something called URLLC, ultra reliable low latency communications. This again is a guaranteed latency system over the cellular network. We do know there are chip vendors working at the moment on integrating TSN and URLLC. And one of the big target markets for that, obviously automation, but the biggest one is autonomous vehicles.
Yeah, we've already got a number of 5G routers in the market, so I know we're tracking those developments pretty closely.
Oh, absolutely. It's 3GPP version 16, which defines the URLLC standards. It's slow on the rollout, but what do you expect? This is a major technology jump that we're actually delivering here. So it's going to take time, but you can see this happening, and especially in the automotive world, TSN on the component level with inside your car is already being implemented simply because of the guaranteed delivery, low latency.
Yeah, I think there's a definite trend that the chipsets are going to become more ubiquitous, and that means they're going to become cheaper, which means we're going to start finding them in much lower order switches and routers and everything. Peter, from the application and business viewpoint, where will TSN take us in the future?
I think what Brandon already mentioned is actually really the key for this success of TSN. It's used in so many different application areas, industries. Even I'm more from automation. It's clear that we all benefit from having a mainstream technology that is supported by all these chip vendors and let's say the toolkit providers that work on drivers and software for these chips. So we have it in automotive, audio, video, transportation. This is really bringing also automation in that direction to get away from, I called it, all these ecosystems at the beginning. Really work towards a common ecosystem and really concentrate on the applications. And not everyone is developing similar solutions for solving things that are already part of standards. We see already existing, let's say, solution providers moving to TSN in automation. So this can give us a confidence that this is fully understood by all the major automation suppliers. So this is creating a big momentum. And I think looking at the factories and plants, TSN will really enable these more flexible, these more reliable productions, where the network is granting certain quality of service to the applications, what we typically call the plug and produce concepts for the industry. And then certainly, I don't want to forget, as mentioned before, that TSN is the network, and we need certainly the higher layer harmonization as well with OPC that is fully transport agnostic and can work on top of such standards. Brandon mentioned an important thing. We talked today more about the wired connectivity also in automation, but wireless is another key in future, making the flexibility in production. So it's not only about that 5G or in future 6G, it's also Wi-Fi 6, Wi-Fi 7. So we will have much more flexible options in communication.
Yeah, Peter, you're absolutely spot on there. I mean, at the end of the day, TSN is an absolutely fabulous development by the IEEE. There's no questions about it. I mean, the deterministic delivery is critical and key, and it's a standard. But you still need to talk with the higher layer protocols. And, you know, as I mentioned, and as Peter just mentioned a minute ago, you know, TSN also will become transport agnostic. It will go over cellular. It will go over some form of Wi-Fi at the end of the day. And we're just at the early, I wouldn't say the early stages. We already have TSN implementations alive and well and doing things, but it's a developing standard. And you know, the key thing at the end of the day is that word standard. It will interoperate.
Well, gentlemen, thank you very much for your contributions. I think we've covered a lot of interesting ground on what I hope our audience will agree is an important technology for the future. Advantech is obviously committed to TSN and already has a number of products available for users who want to implement systems. Brendan, perhaps you can just give us a brief overview of what's available today and what's coming along in the near future.
Oh, sure, no problems. I mean, we've already launched a TSN Edge switch, and as I think I mentioned earlier, we have this live in production arenas with machine builders. Following on from the Edge switch, we're also looking at creating a TSN core switch, and you know, core obviously is a wonderful word to use. The reason we use the word core is obviously we have higher speed uplinks than the typical 100 meg or even gigabit that you'd use in the machine. And then obviously layer 3 capabilities. And to ensure that we can also approach another market we haven't talked about, which is the power and energy market, we'll look at the power and energy style redundancy systems. From the IPC, industrial PC side of things, we already have an IPC which is TSN compliant, so all the necessary stream classification is done within the actual IPC. And there's also a version available for railroad, or will be available for railroad or transportation applications. And then finally, finishing off with transportation applications, I mentioned earlier the Ethernet train approach, where we have a time-sensitive bus. We are also developing TSN compliant train switch as well. So yeah, as I said earlier on, as opposed to having 3, possibly 4 different physical networks on your train, we can all make it into one physical network using a TSN train switch.
Cool. I think the IPC stuff's particularly interesting because that's going to open the possibilities for users to start developing TSN native edge devices and gateways. So it's nice to know we're doing stuff there beside on top of the switch stuff and 5G stuff that you'd expect. Well, that wraps up our session for today. I hope you found something interesting in our discussion, and I'd like to thank Brendan and Peter for sharing their experience and insights. If you're thinking of moving towards a TSN solution and want to find out more, then you'll see links to relevant contacts and information on the screen now. I'd like to thank all of you for taking the time to listen to us and look forward to welcoming you on the next InnoTalks session. But for now, it just remains for me to say goodbye.